Okay. Since it's both of y'all, I probably wouldn't be asking for G's in the chat. I'd be asking y'all to answer out loud if that's okay. All right. All right. I'm going to see something here. Right. That's, oh, why does that throttle down all the way there? Okay. Maybe we can do this. Do that too. All right. Hold on. My son was interfering with some stuff when you were sitting there. That looks fine. That looks fine too. Okay. Maybe we could do that. Okay. Yeah. I think y'all should be hearing me still. All right. So, ladies, good evening. Good to be back. So with Mishka, what y'all would have been doing recently was kinematics. And with kinematics, y'all would have been working on some differentiation and some integration. So usually what I do is I kind of use that as a bit of a segue into revising differentiation and thus integration thereafter. Right? But seeing as she would have done some of that stuff, well, basics of differentiation, I'll use that as a bit of a springboard, right? Now, of course, if as we go along anything is given trouble, please feel free to let me know, right? That's not a problem, right? So I won't be going over everything from all the way from scratch, like how I do in the July, August, right? But I have some notes here from last year that I will use just to kind of point out some stuff, right? So remember, differentiation, one of the parts of calculus, founded initially by Sir Isaac Newton, and then later also independently discovered by Gottfried Leibniz of Germany, right? And of course, there was a bit of a priority dispute because the great Sir Newton did not publish his findings. He liked to keep things to himself, certain things. And then Leibniz did publish. So people knew Leibniz's work and associated it with calculus. And hey, Aditi, how are you going? Good to see you on. Yeah, so there was a bit of a dispute, and it was settled by the Royal Society for the Arts or the Sciences in England. And who was it that was the president or in charge of the Royal Society but Sir Isaac Newton himself? So himself unto himself. So it's quite an interesting story, right? Calculus is actually in my opinion, one of the most important discoveries humans have made, because it unlocked a lot of things for us. But again, I don't know the full story that well to recount it. I did at a point in time when in the pandemic I was doing some more reading about these things, and I really think someone should do like a Netflix series to make it seem a bit more interesting, and maybe students might have a bit more of an appreciation. But anyhow, right, so we use differentiation to find the gradient of non-linear functions. So a linear function is one that looks like this, a straight line function. And as we know, right, the gradient, right, as people like to say, the slope of the line, right, is a constant, right? So along a straight line, the rate of change of y with respect to x, so the rate of change, the change in y, or given a change in x, right, y2 minus y1 over x2 minus x1, is a constant. You can take any 2 points along a linear function, use them to find the gradient, and you will get the same value regardless of which points you use, right? Now, with a nonlinear function, the gradient is constantly changing, right? And how they decided to find the gradient of a nonlinear function was to draw a tangent, right? That orange line is a tangent, which is a line that touches the function, the nonlinear function, at one point. And therefore, at that point, the tangent and the curve, the nonlinear function, have the same gradient, right? So, of course, it was a bit, cumbersome to have to draw the nonlinear function and then accurately draw a tangent to a single point where you wanted to find the gradient, and then to have to repeat that every time you wanted to find the gradient of a nonlinear function at a different point. Oh, evening, Yana, how are you doing? Good to see you again. Right. Now, the question became, okay, so the gradient is constantly changing, right? And dy dx is how we notate. This is actually Leibniz's notation, right? Newton had a different notation, right? So if y was g of x, his notation was oh, hold on, sorry. Why did it get, okay, no, y'all didn't see that. Okay, yeah, no, it became dimmer on my side, and I have no idea why. It was very bright just now, right? So the what you call it? He did g prime or g complement x, something along those lines, right? So that was Leibniz's note. Actually, I think Newton. I think he used the dash or the dots. It was one of them. Yeah, so that one became a little. It was easy to use Leibniz's notation. So that's whose notation we normally use with calculus, right? So dy dx became an expression for the gradient of a nonlinear function at a point, and we call that the derivative of y with respect to x, right? I use that phrase more now than the differential of y with respect to x because I was told that the derivative and the differential are two different things by a teacher from the States who I was liaising with on not WhatsApp, sorry, Instagram, right? Her handle is Calculuscious. Luscious. Right? And she has some interesting math stuff there. All right. Hey Zane, what's going on? And they love shorty. What vibes? All right, good night to you all. Yeah. So, well, yeah, clearly, well, her degree is clearly maths and mine is not. All right. Yeah, I cool. Let's run a little bit of class. I'm trying to accelerate the process here. Yeah. So, there is a way to do it and to show you how they came up with it, but your syllabus is specific about not showing you all differentiation from first principles, which to me is a bit of a crime, but we'll move past that for now. So the basic kind of algorithm with differentiation or finding derivatives is if you have a function y is equal to a, which is multiplied by x to the power n, to find the derivative of y with respect to x, so you have to multiply the index to the front, as you can see across here, and then decrease the index by 1. So differentiation begins with a D, as does the word decrease, right? Sorry, is this add maths? Yes, it is add maths. That's correct. Right. So, like for here, for x to the power of 4, right? So to find the derivative of y with respect to x, we multiply the 4 to the front, and we decrease the index by 1, and 4 minus 3. 4 minus 1 is equal to 3, right? So you could show it long ways. I mean, 4. Well, you had to know this, right? So you could take a look. You don't have to, right? Or you could always come back in the July, August when I do it from scratch. Right. So you multiply the 4 to the front, you decrease the index by 1. So the derivative of x to the power 4 with respect to x is 4x to the power 3. Right? Now, and what this actually is for this function, x to the power 4, which actually kind of looks like this. Right? Hold on, sorry. Yeah. No. Philip, right. Right? This item here is actually what we call the gradient function. The gradient function is the function that we use to find the gradient of nonlinear functions at different points along them. So like if this was x is equal to 1, x is equal to 2, x is equal to 3 on the top there, you'll plug those values of x inside of there and find the actual value of the gradient at that point. Because remember, the gradient of a nonlinear function is different at every point. All right. So what about this one here? Y is equal to 3x squared. All right. So if we had to find here the derivative of y with respect to x. All right. So Julie, what would it be? You multiply 2 by 3, we would get 6x, right? And of course, when you decrease the index by 1, 2 minus 1 is 1, but we don't show the power of 1. All right, so just 6 by x, right? Now here we have a polynomial, right? A polynomial being like a quadratic, a cubic, an expression with multiple terms, right? And all we have to do here is find the derivative of each term one at a time, right? So I hoping Shamari will help me out here a little bit, right? So if we found the derivative of x squared with respect to x, Shamari, what would it be? It must be 2x, exactly. Because you multiply the 2 to the front, and when you decrease the index by 1, you get 1. Right? Now the power here of to which x is just 1. Right? So 1 by minus 4 will just give us back minus 4. And check this. If we decrease the index by 1, 1 minus 1 is x to the 0. And any base raised to the power 0 is 1. Right? So there's no x term here. And then on top of that, right, we also have to consider, what about this minus 1? So that minus 1 is called a constant, right? In other words, it's a term independent of x, to which no x variable or to which any variable is attached. So the value does not depend on the value of anything else. It's a constant value, hence it would constant, right? So with the minus 1, right, so there's no x value there. So you could consider that it's minus 1 by 1. And then you could pull from above and say, okay, well, that's minus 1 by x to the power 0. And when you multiply 0 to the front, you get 0. And it wouldn't matter if you decrease the index by 1 and get x to the minus 1, because 0 by that will just give us back 0. And hence the note there is that the derivative of a constant is equal to 0. Cool. Nice. Okay, so this would be the derivative of this function with respect to x. Okay, cool. Now we have some slightly different looking ones. Give me 1 second. Let me see how much room I have on this page. Oh, it is already split into 2 pages, really? I didn't realize that. Okay, all right. Well, I guess it can't hurt to do that. Anyhow, small thing. Okay, so this function here, in order to find its derivative, what we have to do is apply laws of indices and make this 3 by x to the power minus 2. Right, now when we do that, and we find the derivative of y with respect to x. So when you multiply minus 2 to the front, a minus by a plus is a minus. So minus 2 by 3 is minus 6. And when you decrease the index by 1, you are subtracting 1 from it. And minus 2 minus 1 is minus 3. So you could always write this back as minus 6 over x cubed if you felt so inclined. You don't have to, but you could. All right? Right, now this last one here, right, what we'll do is, again, we'll use laws of indices to put it as x to the power of a half. Right, so of course, these two things, kind of make you question what is the meaning of raising to a power. Because you can't really multiply a half of something. Well, sorry, you can't multiply 1/2 instance of it. So clearly there's some different meaning to the word index we have to understand here. Okay, so when you multiply the half to the front, you're going to get a half. But when you decrease a half by 1, a half minus 1 is minus a half. Right, so then that could go below. So you can end up with 1 over 2 by x to the half. And of course, if you apply your laws of indices, you get 1 over 2 by root x. All right, so we have lots of little bits and pieces you have to remember here. And the laws of indices are actually quite important as well. Okay. Dana, C. Hey, Dana, how are you doing? All right, cool. All right. So, Shamari, are you okay with the example so far? All right, Julie, what about you? Any questions? Are we good? Good. Okay, cool. Right. So the past papers don't have too many questions, but we have just basic differentiation to do. So what we're going to do right away is move into what we call the chain rule for composite functions. All right. I was actually working this recently with some other the Form 4 holy name girls. All right. So when we have a composite function, so basically you have a function raised to a power, right? So one thing you could do is you could actually expand the bracket. So let's say it was 2x plus 3 squared. You could expand that quadratic, right? Sorry, you could expand and get a quadratic, and then you could basically differentiate or find the derivative of each of the terms inside, right? However, if you have powers higher than 2, like even cubics you could do, but quartics, quintics, and anything to the power 7 or over, it becomes very cumbersome to try and expand that. I mean, it could be fun if you know binomial theorem or Pascal's triangle, but seeing as those things aren't taught anymore at the O level, which I think is a crime, we have this little shortcut. So what we do, or what I like to explain, is that to find the derivative of y with respect to x here, so I like to say differentiate the outside and then differentiate the inside. So find the derivative of the out. What does that mean, the outside? So we have a power here. What was the protocol before? We multiply the index to the front, and then we decrease the index by 1, right? So we find the derivative of the outside, and then we also have to multiply by the derivative of the inside, right? So this is just ax plus b, so the derivative there would be just a, right? Right, so a, and a is, sorry, the derivative of the inside. Right, now with differentiation, right, the inside here, as you can see, it's a linear function, like it's in the form mx plus c, like a straight line function, but it could be nonlinear as well. All right, so that works for differentiation. Okay, so you could always actually simplify it a bit more. So if you multiply a by n, you're going to get an, sorry, that n then come out to n-ish. Right, an by ax plus b, the n minus 1. Okay, interesting. All right. So, like with the examples down here, let's do a couple of them, right? Wait, could you stop moving? Right, thank you. Oh, hey, afternoon, how are you doing? I don't have a name, I just have it. Looks like Pocahontas. Thing and a peace sign. Not sure what to call it. Anyway, right. So here, if we find the derivative of y with respect to x. So this one is relatively straightforward. So we're going to multiply the index to the front. You get 4. Right? You don't do anything to the item inside the bracket. And then you decrease the index by 1. 4 minus 1 will give us 3. Ariana. Well, good night, Ariana. Nice to have you on. Okay. And then we also multiply by the derivative of inside the bracket. And as you can see, there's a nice, simple linear function. The derivative of 3x is just 3. 2 is a constant, the derivative of which is equal to 0. Right, and now we multiply the 3 by the 4, and we can get 12, then multiplied by 3x plus 2. Then, oops, that bracket kind of didn't form properly. Right, then cute, lovely. Right, now with this item in the blue, do I want to use that blue? I guess I will. Right, so here what we'll do again is we use laws of indices. So 1 over the square of 1 minus 4x can be written as 1 minus 4x to the minus 2. Right? Now, sorry, I thought I would have caused it to turn. Right, there you go. Right, so when we now find the derivative of y with respect to x, so you multiply the minus 2 to the front, so minus 2, then multiply by 1 minus 4x. And then when you decrease the index by 1 minus 2, minus 1 is minus 3. And you have to multiply by the derivative of inside. So the derivative of a constant is 0, and the derivative of minus 4x with respect to x is just minus 4. And now when you multiply a negative by a negative, what do we get? We get a positive. So we get 8, then multiplied by 1 minus 4x to the minus 3, which is fine if you leave it as such, or if you prefer, the bracket can go below and negative sign will be kind of used up. So you have 8 over 1 minus 4x, which that denominator is cubed. Okay, and we have one more example for the road, and then you'll get to try some. So what I did was I went through the past papers and I pulled out like all the chain rule items. Then we'll do product rule, which you only have a few of those as well. Then you have quotient rule, which you have even less of those. We have some trig stuff to do, which we'll go through quickly. And then we have some the longer ones. So the ones that appear most often are the stationary points, as you can see here, equations of tangents and normals, and they have a few rates of change, right? Now, I don't expect to get through everything today, but this could always feed across into next week, Tuesday, all right? Again, we're also not bound to do every single question. If we do all, then the better for you. But again, we have to wait against, we have other things to complete, and then mock is very soon, and we have other topics to revise. But when we revise this, this is revision for the exam in May as well. All right. Sorry, where was I? Right. Okay, so chain rule. Right. So this one here, this one is in the orange. Right. So how we will rewrite this item here is using laws of indices. So it's the square root. So it becomes 3x squared minus 2x, then raised to the power half. All right. So this is actually the only example that we have currently where the inside of the bracket, the core, I guess you could say, is actually a nonlinear function. So when you're finding the derivative there, it's not going to just be a single coefficient. It's going to be a little more. Right, so this item, you multiply the index to the front. So you have a half, then multiplied by 3x squared minus 2x. When you decrease this by 1, a half minus 1 will give us minus a half. Sorry, 1 second. And then you're going to multiply that by the derivative of inside the bracket. So the derivative of 3x squared will be 2 by 3 is 6. And x to the 1, and the derivative of minus 2x with respect to x is just minus 2. Right, my head blocking, I didn't realize. Okay, right, and then we could go a little further here. So you could have a half multiplied by 6x minus 2. then multiplied by 3x squared minus 2x to the minus a half. Let me just check to see if I have more. Oh, yeah, I have enough room on this page to go. Right. So you can multiply the half by both terms on the inside there. A half by 6x is 3x. A half by minus 2 is minus 1. And then you could put this item below, right? You could have 3x squared, then minus 2x to the power of a half. And you could always rewrite it like this, using the actual laws of indices. And the power of a half thus becoming a square root. 3x squared minus 2x. Okay, cool. So what I'm going to do, I'm actually going to take a picture of this and send it in the chat for you guys to have the examples, right? If, of course, you're copying it down and you want a few more minutes to do so, you can let me know, right? Boom. Let me see. Was it a good picture? It looks very, very light. I guess you could zoom in and check it out a bit more. Okay. All right. Okay, Julie, how are we feeling with that stuff so far for chain rule? Any questions on any of them, or we good with all? All right, sure. Oh, yeah, no problem. All right, and Shamari, how about you? How are you feeling with the examples on the screen there? Any questions, any problems or issues? Sorry? Okay, I understand. All right, good, lovely. All right. Hey, I'm Kamara. How are you doing? Hello, Emily. How are you? Danny. I feel like I know Danny. Hey, Kimo. All right, Emily. Tell you, hey, Chantal, how you going? This microphone interfering with that much. No problem. Ooh. Oh, that was nice. All right. Okay, cool. All right, so we just have three questions from the past papers. We have 2016, 2019, and 2024, right? The 2024 differentiation questions were kind of weird. This is the only kind of decent one from them, right? So, right, so for this one, clearly what you're going to have to do first is you're going to have to rewrite y using the laws of indices. So you're going to have 5x squared minus 4, then raised to the power of a half. Okay, cool. So I'll give you guys a minute or two to find the derivative of that item. Right? Of course, if you're having trouble, it's not a problem. You're not under exam conditions. I know I went through some examples, but that don't mean that you understood everything as well as you should. And sometimes things just do compute. So if you have any questions, please feel free to let me know. All right. Just timing myself here. Well, thanks for sharing that, Emily. And thanks for following. Start here. Little arrow going across on this side here. So we want to find the derivative of y with respect to x. Okay, cool. Right. All right. Okay. So Julie, talk to me. What's the first line you should have here? If you're ready, you ready? All right. Go ahead. Right. Good. Hold on. You're missing something here. Power. Very good. Right. Yeah. When you find the derivative of inside the bracket, what do we get? 10x. Very good. Yeah, because the derivative of minus 4 is 0 because it's a constant. Okay, and when we simplify and you multiply a half by 10x, what do we get? Yep, you get 5x. Then multiplied by 5x squared minus 4, which, hold on, sorry. 5x squared minus 4, which itself is raised to the power of minus a half. And there's one more thing you could do here. But did you stop here or did you express this differently? Yep, that's correct. 5x squared minus 4, then raised to the power of a half. And the only other thing that I would advise you do with this is you could use laws of indices to put the square, but that's not necessary, right? Stopping here is fine as far as I'm concerned. I would prefer something like this, but this is not wrong or incomplete. All right? Okay. All right, Shamari, how are you feeling with this one? All right, cool. All right, so 2019, we have differentiate the cube root of 2x plus 3 then squared with respect to x, giving you an answer in its simplest form. Right. So first, what we have to do is you have to kind of let y, sorry, I said the word let and I did not write it, right? We have to let y equal to the cube root of 2x plus 3, sorry, 1 second, right, then squared. Now here, to simplify this, right? So if the square root can be expressed as the power of a half, the cube root can be expressed as what power? Power of 1 over 3. Right? So whatever is what we call the order or the power of the root, that becomes the denominator of what we call the unit fraction, the power to which we convert it. And then with laws of indices, when you have a power inside a bracket and a power on the outside, you multiply those two things together. So 2 by 1/3. So 2 multiplied by 1/3 would give us, so of course, when you multiply in fractions with the protocol, you multiply numerators together, 2 by 1 is 2, and you multiply denominators together. 1 by 3 is 3. So we have the power of 2. So we have 2x plus 3, then raised to the power 2/3. And that is the item for which you're finding the derivative. Okay, so sorry, I didn't mean to do too much of the work there, but I'll give you guys a minute or two with that one, and then we'll correct and move on to the 2024 question. And after that, we're going to tackle chain rule. little. Okay, so we want to find the derivative of y. Sorry, one sec. Come on, Philip. Okay. With respect to x, dy dx. Okay, cool. All right, so Shamari, tell me what the first line of the working would be, please. If you're ready. Okay, cool. So the basic process with the derivatives is we multiply the index to the front, right? What's the index here? What is that item? 2/3, right? So you multiply the 2/3 to the front, right? So we have any bracket. So the contents of the bracket do not change. And then we have to decrease the index by 1. So that's 2/3 minus 1. In addition to which, we have to multiply all of that by the derivative of inside of the bracket, all right? So let's talk about that. So if you were to find the derivative of 2x, what would you get? 2, and 3 is a constant, the derivative of which is equal to 0. So all we'll be doing here is multiplying by 2. All right. Okay. Are you okay with what I just did? Okay, cool. Any questions at all? All right. Now we'll simplify by multiplying the 2/3 by the 2. So that's 2/3, then multiplied by 2, then multiplied by 2x plus 3. Now 2/3 minus 1, right? That's like saying 2/3 minus 3/3, right? So 2/3 minus 3/3. So that's like 2 minus 3 over 3. Sorry, 2 minus 3 over 3. Minus 1. There you go. Right, so we have minus 1/3. Now, of course, when you're multiplying fractions, you multiply numerators together, then denominators together. 2 by 2 would give us 4. 3 by 1 will give us 3. And here we have 2x plus 3 to the minus 1/3. Are we okay up to that point? All right, cool. Now, we could go a bit further if necessary. So, of course, there's multiplication understood. And this item here, which is raised to a negative 1/3, could be written as this. You could invert it. And then again, you could simplify by multiplying the fractions together. Numerator by numerator is 4. And of course, then you have 3 then multiplied by 2x plus 3 itself raised to the 1/3, right? I was just leaving it there. The only other thing you could do thereafter is you could use the power of 1/3 and laws of indices to change that to the cube root. It'll be 3 then multiplied by the cube root of 2x plus 3, right? But I don't think you have to go all the way there. You should be able to, but you don't always have to, right? This is a perfectly good stopping point. Okay, all right, so Shamir, are you okay with that item there? All right. Julie, what about you? Talk to me. Julie, you there? All right, you okay? I didn't hear you. Yeah. Okay, cool. All right, so let me. All right, so let me. As in, like here? Oh, like here? Oh, yeah. All that's good. That's more than enough. Like I say, once you get up to here, you're golden. Anything past that is gravy, right? But I'm glad you were able and you did go past that point. Let me just send a picture of this one in the chat too. Hold on, what was the previous thing I sent? Oh, I didn't send a picture of 2016. All right, so let me send a picture of that one time. All right. I think I'll just send the PDF after. Yes, these pictures not coming out too great. I'm not entirely sure why. Okay, cool. Right, so we have one more of this, right? So we have the 2024. So the equation of a curve is given by y equal to 5x squared minus 7 to the power 4. The determine the equation of the gradient of the curve. So again, we have a curve. The gradient of a curve is given by finding the derivative of the function itself. So long story short, they want you to find dy dx, or an expression for dy dx, right? So again, I'll give you a minute or so to organize that, and then we will go on to the product rule. Oh, that's for sure. So let me, what was the color here? So we're going to go with blue now. Yeah, blue is fine. Right. So y, sorry, my writing is a bit atrocious today, more than usual. Right. Y is equal to 5x squared minus 7, then raised to the power 4. Okay. All right. Shamari, you want to try your hand at this one? All right. So talk me through. Mhm. Right. Right. Very good. Yeah, there you go. And then to simplify, we're just going to multiply 10x by 4 and get 40x. Sorry, 1 second. All right, 40x, then multiplied by 5x squared minus 7, then cubed. All right, okay. So that one was a little better then. All right, cool. Julie, what about you? You cool with that one? Julie. Yeah, she's somewhere. All right. Okay. All right, so the 2024, that question, right? So when you say in the format that we did for the last one, oh, well, that was because here you had a negative index and the index was rational, right? When you have a negative index, you could that the index, the item to which the index is attached, could become a denominator in its own fraction. And then a rational index, which is a fraction, could then basically, using the laws of indices, be used to convert to a particular root, right? But this item here didn't have anything like that. Do you see any stream? Yeah, I see any stream. Okay, no. Yeah. So wait, hold on. Just now. Oh yeah, sorry. Yeah, okay, cool. Right. Yeah. So what I was saying is what was it? Right. In this one, we had a positive index and it was a whole number. So we didn't really have much scope to express it in different ways. So that's all that could really be done with it. You okay there? All right, cool. Yeah. Ariana, what was the story? Everything cool? All right, so product rule. So y is equal to u. All right, so the product rule. So what we're going to take a look at now is another special rule with differentiation where we have a product of two factors. All right. So there's a kind of a formula that you could apply, right? So if y is equal to the product of two factors, conventionally we use u by v, then dy dx, the derivative of y with respect to x, is equal to v multiplied by du dx plus u then multiplied by dv dx, right? So again, it's a bit of a formula you kind of had to remember. And then this word here is or, right? So you could also write it as v multiplied by u complement plus u multiplied by v complement. Yeah. So let's try it down here with this item in pink, right? So clearly we want this item to be the u and it's being multiplied by this item, which is the v. So what some people, including myself, like to do is if we know that we have a product, which we do, right? Because we have this item being multiplied by a next item. So they're like two different functions being multiplied. So clearly we have to apply the product rule. So dy dx is equal to v multiplied by du dx plus u then multiplied by dv dx. So let's talk about du dx, right? Du dx is the derivative of 3x squared with respect to x. So you're going to multiply the index to the front. 2 by 3 will give us 6. And then we're going to decrease the index by 1. 2 minus 1 is just 1. So we have 6x. Sorry. Right. And then the dv dx one, right? So that one, hold on. Yeah. So dv dx. So that one is this item here, which is a composite function, right? So you multiply the 3 to the front of the bracket. You have x plus 3 on the inside. You decrease the power by 1. 3 minus 1 is 2. And we multiply by the derivative of inside of the bracket, which of course is just in this case 1, which doesn't change anything. All right, so now we could take our formula and our items there and plug them into the working, right? So we have v, which is this, by du dx, right? So we have x plus 3 cubed by 6x plus u by dv dx, right? So u, which is 3x squared, then multiplied by dv dx, 3 by the square of x plus 3. Right, so if you can get to at least here, most of your work, your differentiation is done, right? Now, to simplify, we could put that 6x to the front, right? So you could have 6x by x plus 3 cubed. Of course, 3x squared by 3 will give us 9x squared, then multiply by x plus 3 squared. Right? So this is CSEC maths. Smiley, this is odd maths. CSEC odd maths, actually. Yeah. Right. So if you can get up to this point, you're basically good. All right. You can actually go further and simplify using factorization. Right. So this is the part that does give people a bit of issues. It's not actually that hard if you take your time because you know how to factorize. We just sometimes don't really expect it here. Right. But yeah, factorization like salt, boy, not on quadratics. So what I suggest, look at the coefficients between 6x and 9x squared. Between 6 and 9, the highest common factor is 3. And between x and x squared, the highest common factor is x. Right? Now remember, what I'm doing here is kind of optional. I would suggest you do learn how to do it eventually. But again, if you could just get at least these first two lines, you get most, if not all, your marks, right? Okay. And then if you look at the bracket, you have x plus 3 cubed and x plus 3 squared. So it's like if you had y cubed and y squared, we know that the item with the lower power is always the highest common factor. When you factor and you divide, you get y plus 1, because you divide this by y squared and get y. And when you divide y squared by itself, you get 1. Right? So what we would do here is we would pull the bracket, the entire bracket, right? And we would apply the lower of the two powers, which is the square one. And now we will divide. So 6x divided by 3x would simply give us 2. And x plus 3 cubed divided by x plus 3 squared is just going to give us x plus 3. Now, 9x squared divided by 3x is just going to give us 3x. And of course, x plus 3 squared divided by itself will cancel to 1. Right? Now here, you could do a little simplification. So 2 by x, 2x, and 2 by 3 is 6. And when you add 3x, you're going to get 5x plus 6. So your final answer will be 3x by x plus 3 squared by 5x plus 6. Right? So again, yeah, it could be a lot to kind of stomach the factorization and simplification. So if you could get at least these first two lines going, you're mostly good, right? If you could finish off, then great, right? Well, you could work up to that. Okay, now I'm going to do a second example, which is a little more involved because as you can see, hold on. Sorry. Yeah, as you can see, we have two composite functions. All right. So we know that we want to find the derivative of y with respect to x here. And this is, of course, this is a product. So we're going to have v then multiplied by du dx plus u then multiplied by dv dx. Hey, Takuma, thanks for sharing. Right. So let's find those derivatives before jumping into the actual item, right? Right, so if you want to define du dx, so this one here, so you'd multiply the 2 to the front, the 1 minus 3x inside doesn't change, the 2 minus 1 will give us back 1, but interestingly enough, when you find the derivative of inside the bracket, you're going to get minus 3. And when you multiply minus 3 by the 2 in the front, you're going to end up with minus 6, hold on one second, right, minus 6 by 1 minus 3x. Right? Now you could leave it like that or you could expand it, up to you. Right? Now the next item, which is dv dx, this one here. So again, we're going to multiply the index to the front, so 3. Right? Inside the bracket does not change. We're going to decrease the index by 1. 3 minus 1 is 2. And we're going to multiply by the derivative of inside the bracket, which is just going to give us 2. Right, so when you multiply the 3 in the front by the 2 in the back, we get 6 by 2x plus 5 then squared. All right. Now we're not done. We had to go and plug in those things into the formula now, right? Okay, so in the first case, v by du dx. So that's v and that's du dx. So v is 2x plus 5 then cubed. Du dx is minus 6 by 1 minus 3x plus u by dv dx. Right. So that's 1 minus 3x all squared. So that's u, and then dv dx. Those little dots I'm putting mean multiply, by the way, right? So you could use those to represent multiply, or you could use a multiply sign. It's just that, of course, takes up a little more room, so it's a little more visually expensive. You don't want to clutter up your visual space any more than necessary. Right? But again, I think it's more of a style choice. Right, so again, if you could get to this point, the majority of your work is done, right? The next line could be the final line. So I'm going to bring the minus 6 to the front here, followed by 1 minus 3x. And I'm going to put the 2x plus 5 then cubed here, right? Plus, so again, I'm going to put the 6 to the front here, and then 1 minus 3x then squared, and then 2x plus 5 itself squared. Right? So once you kick it up to there, again, you get most of your marks. If you could now do the, what you call it? I don't know what color to use here, boy. Green would have been the better one to use there as the inverse of that color. Anyway, sorry, I'll use the blue. Yeah. If you can do the factorization, then by all means, right? So between minus 6 and 6, you could pull either one. You could pull minus 6 or positive 6. Let's use 6. Between 1 minus 3x, which is to the power 1, and then 1 minus 3x squared, we'll use 1 minus 3x. And between 2x plus 5 cubed and 2x plus 5 squared, we'll just use the one with the lower power, 2x plus 5 squared. Right? And of course, in the larger bracket, now when you now factorize, so minus 6 divided by positive 6 is just minus 1. 1 minus 3x divided into itself will cancel. And then 2x plus 5 cubed divided by 2x plus 5 squared will just give us back 2x plus 5 to the power 1. All right? Now, 6 divided by 6 will give us 1. 1 minus 3x squared divided by 1 minus 3x to the power 1 will give us 1 minus 3x. And 2x plus 5 squared divided by itself will cancel to 1. Right, okay. When we expand on the inside, minus 1 by 2x minus 1 by 5 plus 1 minus 3x. Right, so what's going to happen here is as follows, right? So we're going to have 6 by 1 minus 3x, then again by 2x plus 5 squared. So minus 2x minus 3x is minus 5x. Minus 5 plus 1 is minus 4. Right? So again, the stuff in the blue is nice to be able to do, but it's not entirely necessary at this point. I don't want to say that. I prefer you all try to do it, but again, I understand we're doing revision. It might be a little rusty, a little new. All right. So do what you could do. All right. Okay. So what I'm gonna do, I'm gonna take a couple of pictures from this page and send in the chat. I'm gonna try and send you whole page because I find, again, pictures not coming out as great as that. Actually, I wipe the lens. I don't know. Okay, I thought I zoomed out sufficiently. Like our old man trying to take a picture here, boy. That old. Right, and the second picture. So what other rules have you done so far? Just the chain rule. This is product rule, and then up next will be quotient rule. We're gonna do a couple of questions on product rule now. I'm just gonna check out my class there and see if they're okay. All right. Okay. So Julia and Shamari. All right. So with this first example here, with the pink, do we have any questions? Do you have any questions? Are you okay with the stuff in the pink to the top of the page? All right. Shamari, what about you? Are you okay with the stuff at the top? Example 1? All right, cool. All right. What about example 2? Any questions or you're all okay with that? All right, cool. Julia, what about you? Sorry. Yeah, yeah. You want this one or you want the other one too? All right, cool. Let me know when you're ready, right? Right then, boy. Oh no, that is an X, but it looks like a U, and I'll see what you're saying there. Yeah, yeah. Just the way I wrote it very poorly. All right, is that more X-like now? More X-ish. All right, cool. Can I go on to the next page, Julie, or we are met again? All right, cool. All right, so there are only three questions, as you could see, so we'll try to do all, okay? So it says differentiate the following with respect to x, simplifying your result as far as possible. Okay, so we're going to let y equal to 5 minus 2x, sorry, then multiplied by 1 plus x to the power 4. All right, so of course, this is the u, this is the v. It doesn't actually matter, right? Okay, so I'll give you a couple of minutes to try that one, and then we'll go through it. All right, so hopefully we get to finish these three and then try quotient rule, and we might probably end there for the night. Somebody name page or like a page number or Ariana, what's up? I see a page. Is that one of your friends? Oh, all right, cool, no problems. Yeah. Mm-hmm. Like here, yeah. If you did that, is not wrong. It just means that the subsequent factorization wouldn't really happen. So you would get minus 6 plus 18x, and then you wouldn't really be able to do anything with that except reverse the differentiation. Sorry, reverse the expansion to then be able to what you call it, factorize. So again, yeah, all stopping here is fine, and expanding that is perfectly fine as well. It wouldn't change the value or the accuracy of the answer. Is that mol? Yeah, mol. Maths or art maths? Art maths. Oh, okay. So I can look at some art myself. Yeah, doing some differentiation tonight. Some revision. Aha. Let me see. Ariana. Ooh, okay. Look. All right, so I'm going to start off by finding, sorry. So of course we want to find the derivative of this particular function, which as you can see is a product. And the derivative of a product will let us use the product rule, which we will write as v, then multiplied by the derivative of u with respect to x plus u by the derivative of v with respect to x. Okay, so let's find those derivatives first. Let's get a different color so things could be a little separate, right? So the derivative of u with respect to x, right? So the derivative of 5, because it's a constant, is 0. And if you find the derivative of minus 2x, you're just going to get minus 2, right? And then for dv dx, so this one here is a composite function, so you're going to multiply the index to the front, leave the inside untouched, decrease the index by 1, and of course multiply by the derivative of inside, which luckily for us is just 1, so it doesn't change anything. All right. Okay. All right. So Shamari and Juliana, are y'all okay so far with the derivatives of each of those factors? All right, cool. So now we're going to plug them inside our derivative down here. So v is 1 plus x then to the power 4 by du dx, which is just minus 2, right? Plus u by dv dx, right? So that's 5 minus 2x then by 4 by 1 plus x cubed, okay? All right, so are we okay with that first line, ladies? Cool. All right, lovely. Okay, so let's see if we can simplify at all. So let's put that minus 2 to the front of the 1 plus x to the power 4. And we can put that 4 to the front here. 5 minus 2x, and then 1 plus x cubed. All right, so stuff in here is fine. If you wanted to, you could, in fact, factorize, but we only have one factor. Well, one item from which you could pull a common factor, right? Which is just that. So it would be, sorry, let me fix that equal sign. It would be 1 plus x, then cubed, right? And any brackets, right? So, well, the minus 2 will just come along. This divided by that, the difference in the powers is 1. So we're just going to have 1 plus x. And then this will cancel with itself, leaving us with the 4, then by 5 minus 2x. All right, cool. So let's see. Expanding inside the bracket here, minus 2 by 1 is minus 2. Then we have minus 2x plus 20 minus 8x, right? If you guys see me make any mistakes, let me know. Sometimes I make that rookie mistake of only multiplying the coefficient by the first term. I know how I do that, but it's happened. Right, so down here we could simplify. So minus 2 plus 20 is 18. And minus 2x, so yeah, minus 2 plus 20 is 18. Right? And then minus 2x minus 8 is minus 10x. Right? You could factor out again, but you don't have to, right? So this would ultimately just be 1 plus x, then cubed, power 3, right? And then 9 minus 5x, right? Okay. 18 minus 10x. And one of the other girls here was saying, this here you could actually factor out the 2 and get 9 minus 5x. And you can put that 2 in the front. So 2 by 1 plus x cubed, right, by 9 minus 5x. Or you can put the 9 minus 5x in front and the 1 plus x cubed behind. All right, lovely. Okay, cool. Good job. All right. Okay, so Maria and Juliana, are you all okay with the solution here? Right, regardless of where this is stopped, are we okay with at least these first two pieces here? All right, cool. All right, cool. Lovely. Okay, on to, sorry, let me see if I can send a picture of that real quick. Okay, So 2011 was actually the specimen paper. The first sitting of CSEC AdMaths was in 2012. Cool. Lovely. All right, 2017. Right, so again, what we're going to do here is we're going to let y equal to 1 plus 2x cubed. Oh, sorry. Wow, I put that in the wrong place. Then multiply by x plus 3. Sorry. So this is clearly a product that u multiplied by v. Okay, cool. So I'll give you a couple of minutes and then we will correct and move on. Thank you, Chrissy. All right, let's take a little swing at this one. Okay, so let's find those. Sorry. We want to find the derivative of y with respect to x. And we're going to use the product rule. So that's v by du dx plus u by dv dx. right? Let's do those calculations on top of here. What calculations? Those derivatives, right? So the derivative of u with respect to x as a composite function. So we're going to multiply the 3 to the front. So we have 3 by 1 plus 2x. We're going to decrease the index by 1 and multiply by the derivative of inside of the bracket, which in this case is 2. So 2 now multiplied by the coefficient of 3. 2 by 3 is 6. So we have 6 by 1 plus 2x then squared, right? And of course, now the derivative of v with respect to x. That's an easy one. That's just 1. So that's not really consideration per se. Okay. So v, we have x plus 3 by du dx. Then by 6 by 1 plus 2x, which is then squared, plus u, which is 1 plus 2x then cubed by dv dx, which of course is just 1. So in simplifying, we could pull that 6 to the front of the x plus 3, which is then multiplied by 1 plus 2x then squared. And of course, the 1 plus 2x then cubed comes along for the ride. Okay, if you get to this point, you're basically home free, right? If you want, you could do the factorization. So let's put that in a different color as well. Right, so the only thing that we can use as, well, the factor would be the 1 plus 2x bracket, and the 1 plus 2x squared is clearly smaller. It's the lower of the two powers, right? Okay, so when we divide this by itself, it cancels, leaving us with the 6 by x plus 3. And 1 plus 2x cubed divided by 1 plus 2x squared will just give us back 1 plus 2x. Right, sorry, here now. Yeah, okay. So 6 by x is 6x, 6 by 3 is 18. And then, of course, it's just 1 plus 2x. So that's going to give us 8x plus 19. Right, so long story short, what we're going to end up with here is 1 plus 2x then squared. Then, again, multiplied by 8x plus 19. All right, cool. All right. Oh, yeah, Rihanna, I agree. Okay, all right. Sean, Marie, and Julie. If you're good with that, let me know. Well, we're not giving G's. Are you all okay with that? All right. If you have any questions, please let me know. All right. Okay. M's. Okay, good job, M's. See? You try, you keep trying, and you take into consideration where you made mistakes and you cater for those, and you try not to make them again, you make progress. Yeah, lovely. Okay. All right, now we have one more here, right? So this one, right? So what we could do here is I'll help a little bit, right? So that root of 4 minus 8x, you can treat that as 4 minus 8x to the power of a half. Right, so this is clearly our u multiplied by our v. Okay, all right. So again, give you a couple of minutes, correct it. All right. This this is she said add maths actually. Yeah, the math is Mondays and Wednesdays from 6:30 to 8:30. If you go on my YouTube channel, I think I have one or two of the latest lives still up there. They won't stay there for long, so you might want to go and check those out. If that's what you're interested in. Oh, thank you for the heart. Yeah, agree. I can all the time. Um, yeah, no problems. Both times it is normal maths. Well, technically it is normal maths, eh? Maths is maths. Pythagoras, Euclid. Wow. Those two of the most prolific math people. 2%. Join back Monday. All right, Ariana. Thanks for joining. Hey, David, how are you doing? Have a good weekend, and thanks for sharing. See you next time. Bye. All right, cool. So let's take a swing at this here. We want to find the derivative of y with respect to x. So we're going to use v by du dx plus u then by dv dx. Okay, cool. So let's go on a side. Oh, come on, man. Philip, that's not what I wanted to do. Give yourself. Right. Let's come on a side and let's find those derivatives, shall we? Right. So the derivative of u with respect to x would just be 2, and the derivative of v with respect to x. Right. So this one, we can multiply the half to the front. You have 4 minus 8x. Then decrease the index by 1, you have minus a half. And then multiply by the derivative of the inside, which is just going to give us minus 8. When you multiply that minus 8 to the front, you're going to get minus 4. Then by 4 minus 8x to the minus a half. So we leave it as it is. Oh yeah, you're going to give it. Leave it as it is because we don't want to. We want to be able to differentiate, and we need to have it in that form. So v, which is now 4 minus 8x to the power of a half by du dx. So that's just 2. V by du dx plus u, which is 2x, by dv dx. So that's by minus 4 by 4 minus 8x, which is itself raised to the power of negative a half. Okay. Now this one is going to be interesting. Right. So we're going to put that 2 to the front here. We have 4 minus 8x to the half plus, so minus 4, right? So minus 4 by 2x will actually give us minus 8x. That is also then by 4 minus 8x, this one being raised to the negative a half. Oh, hey, hi, how are you doing? Does that person have the same thing as Ariana? Anyhow, now, if you got up to this point, that's perfectly fine. You can stop there. If, however, you want to go a bit further, I'm going to show you. Now, between the 2 and the 8 minus 8x, clearly 2 is the common factor. Now, we can clearly see the bracket is the same, 4 minus 8x. Right? What time, everyone? Night? What? Right. So you have a half and you have minus a half. The common factor, the HCF, is always the one with the lower of the two powers, minus a half. Now we're going to divide and factorize. So 2 divided by 2 is 1. Now check this. I'm going to come on a side and I'm going to use a different letter. I'm going to use a different thing. So imagine instead of 4 minus 8x, it was just a. So you have a to the half. And the common factor is a to the minus a half. That's this down here, right? And when you have to factorize, that involves dividing. Now, when we divide and we have the same base, what do we do with the powers? We subtract. And when you minus a minus, it becomes a plus. And a half plus a half is equal to 1. So what's going to happen across here now is you're going to have, all right, so 2, right, 4 minus 8x to the power of 1, which is 4 minus 8x. Now you have minus 8x divided by 2 is minus 4x. And of course, when you divide something by itself, it's just going to cancel, giving us back 1. So it's just going to kind of disappear. All right, so on the outside, we have 2. Then by 4 minus 8x to the minus a half. And on the inside, right, when you draw the bracket, minus 8x minus 4x is minus 12x. That's 4 minus 12x, right? Now you could stop there. That would be probably a good place to do so. If, however, you're feeling frisky, we can continue. What color did I not yet use? Let me use a darker purple. Come on, man, I didn't want to do that. Right, okay. Right, so check it. I'm going to put the 2 here. This item, I'm going to express it as 1 over the root of 4 minus 8x. and that's multiplied by, so I'm going to pull out a 4 here, and I have 1 minus 3x in the bracket. Now, what I'm doing here is not necessary, by the way. It's just something I wanted to show you in case you want to be able to show off and be fancy. Now, down here, this one specifically, what I'm going to do? I'm going to pull out the 4 like a common factor and have 1 minus 2x. And that's going to be square rooted. Now, remember, with surds, this is equal to square root of 4 by square root of 1 minus 2x. And the square root of 4 is 2. Now we have 2 by the root of 1 minus 2x. So now this becomes 2 multiplied by 1 over 2 by the root of 1 minus 2x. Sorry, 1 second. By 4 by 1 minus 3x. And what's going to happen here is this 2 will cancel with that 2. And when you finish kind of multiplying, you're going to have 4 by 1 minus 3x all over the root of 1 minus 2x. All right, so again, anything after the last blue line is not entirely necessary. If you can factorize and get to this line here, that's perfectly fine. You can stop there. Anything after that is just excess and surplus. It's not something that I would consider necessary at this level, but I would always advise you to be able to do it. It's not something beyond you. It is something that an AdMath student should be able to do if necessary. It's just that it's not always going to be necessary. All right, I'm going to send a picture here. Right. Okay, now I was hoping to get through the quotient rule, and had I started on time, I would definitely have done it. But I'm looking at the time. We have less than 7 minutes to go. And I don't think rushing it down now would do it justice. So what I'm going to do is I'm going to leave quotient rule for Tuesday, right? But before we wrap up, so Sha-Marie and Juliana, are you all okay with this item on the screen here? If not, what are your questions? Sorry? I'm gonna hit this chest. I've been confused with the last 2 lines, but I'll figure it out. All right. Are you okay up to like this line here? All right. Okay. If you get to this line here, that's perfectly fine. Like I said, everything after that was just me being extra, right? But you could, like I said, you could always go through it, right? Because, like I said, everything here was attached by multiplication. So I just kind of pull it apart. So this 2 became this 2 over 1. This 4 minus 8x to the minus a half became, well, I applied the laws of indices, right? The negative aspect, put it as a fraction, and the 1/2 became the square root. And this item here, I factorized, I pulled out the 4 and got 1 minus 3x. Right? And then I proceeded to kind of use some surds, some surds working here to simplify that bracket a little bit more. And then I plug it up inside it. Up here, sorry, I was able to cancel the 2's and then go from there. Right? But it's not something you have to be able to do. It's something it would be nice for you to be able to do. Right? Okay. And Julie, what about you? Any questions, comments? Okay. All right. So ladies, I do again apologize for starting late. Yeah, so I think we'll stop there. And when we come back on Tuesday, we'll hit the quotient rule. Seeing trigonometry, the little trick stuff there as well. I might pull that down to the end and add some more stuff there because the stuff in the past papers doesn't really give you a good like exposure to what could possibly come. So yeah, so maybe we'll do quotient rule and hit stationary points. And then on Thursday, we'll do equation of tangents and normals. Right, so this might leak over into a session after that, but we'll figure it out. And then after this, we'll go back into integration, but we'll see when your math exams are. So you all will let me know if you're missing any days, right? But we won't be doing any. I mean, we've basically finished the syllabus, so all we're doing now is revising, right? Anyhow, so ladies, thanks again for joining. If you have any questions and you get to ask during class, please feel free to WhatsApp me and let me know. Other than that, have a good night, have a good weekend, and I'll see you guys next week. Bye. Bye. Right, okay. Why did you put a half at the beginning of the solution? For x3, the shown. as in, okay, hold on. Sure, I'm not sure which particular part you're asking about. Was it 2017, 2011, or was it even further up? Um, I'm not sure specifically which part. Ariana is still there here? Like you're plugging your phone out. But that 2% lasting long. All right. Okay, so thanks for joining. Got a little